So in this video, we're going to talk about the concept of resistors. It's actually going to be the first circuit component that we've looked at that's not a source. So when you think about what a resistor does, if you just need a basic definition that you have to remember, it limits the flow of current. And remember that current is nothing more than the flow of charge. So it basically just makes it hard for charge to flow within a circuit. Now, what is it actually representing? Well, when you see a resistor within an ideal circuit model, what it's representing is a component that's going to take the electrical energy, and remember that power is just the rate at which energy is being provided. So it's going to take the energy in the form of electricity that's being provided to it, and it's going to convert it to heat. So we actually model resistors in a circuit using the equation symbol R. So whenever you see an electrical equation and you see the symbol R, you know that it's referring to resistance. The SI units of resistance are an ohm. Now, one of the things that often confuses people is we abbreviate ohm by the capital Greek letter omega. We don't use an O in that case. And the schematic drawing of a resistor, I've depicted it here to the right. We kind of just have these kind of triangular wave. In fact, if you proceed down the electrical and computer engineering realm, you'll actually see that's what that's called if it's a voltage that varies over time. But really, it's just kind of these series of adjacent lines, and that is the schematic of a resistor. Now the question is, well, what is the relationship between the voltage across the resistor, or the push of current, and the actual current? And it turns out that that equation is known as Ohm's law. And this is really the most fundamental equation of circuit analysis. It's written in its most simplistic form, or most common form, I should say, as V equals IR, or that voltage or push is proportional to current times resistance. However, it's easier to understand that equation if you actually take and solve it for I. So if you solve that equation for I, you'll see that I is equal to V over R. Well, why do I say it's easier that way? Well, remember, I, current, is flow. So how do you get more flow? Well, if you have I written as V over R, you see that it's proportional to V, so that's push. So you get more flow if you have more push. And it's inversely proportional to R. So you get more flow if you have less resistance. Now, another quantity that you will hear of when you take your actual circuit analysis course is this idea of conductance. Conductance, for whatever reason, is denoted by the circuit, the symbol in the equation of G, and it's measured in units of Siemens. And all that the conductance of a component measures is how easy it is for current to flow, as opposed to resistance, which measures how hard it is for current to flow. So let's think about how we can actually do basic circuit analysis applying Ohm's law. So this is the first really complete circuit we've seen. We have an ideal voltage source, which has a rated value of 5 volts. We have a resistor. There's that schematic symbol we saw on the previous slide. Note that its rated value is 1. This K is just kilo, right? That's a metric prefix for 1,000. And this is the capital Greek letter omega. So this is just 1,000 ohms. And what we're asked, we're just going to kind of solve this step by step and trying to determine the current in this circuit. So the first question asks, is the voltage across the resistor the same as the voltage across the terminals of the voltage source? Why or why not? Well, if you hold your hands like this for the two terminals of the voltage source, and you hold your hands like this for the two terminals or points of connection of the resistor, note that those are actually connected in parallel. They share two common points of connection. And remember that when things are in parallel, they have the same voltage across them. So yes, that is in that case. We know that this source is applying 5 volts of push with higher potential on the top and lower potential on the bottom to this resistor. Now, if I have a resistor and I know the resistance value and I know the voltage, how can I find the current? Well, that's just going to be an Ohm's law problem, right? V equals IR, but I want to manipulate that equation in such a way that I can solve for the current. So I say that I, the current, is equal to V divided by R. That's exactly what we were talking about in the last slide. If you have more push, you'll have more flow. If you have more resistance, you'll have less flow because of that proportionality relationship. If you substitute in for V, the voltage across the resistor, which is 5 volts, and you substitute in for R, 1 kilo ohm or 1,000 ohms, what you will find is that result is equal to 0.005 amps. Amps, remember, is the SI unit of current. However, we don't write the quantity typically as 0.005 amps. We would convert it to engineering notation and actually express it as 5 milliamps. So last question, is this current that we just computed the same as the current produced by the voltage source? Why or why not? Well, what that's saying is that if this source provides 5 volts of push across this resistor, which is going to drive a current of 5 milliamps down through this resistor, is that the same current that we actually see in this voltage source? And the answer is yes, because when you only have two elements in a circuit, the voltage source and the resistor, not only are they in parallel naturally, so they have the same voltage across them, but they're also in series. So because of that, that is the actual current through the source in that case. So you can find out how much current is being drawn for that given load out of the source.